Are you able to see it in the presentation mode now?
Yeah.
All right, good. So welcome again. So quickly, we are going to look at the Google's latest model. They announced it around 21st of February. So it's a fairly new model. We have used it for just 2 weeks. None of us are experts at Gemma yet, but this session hopes to kind of really explore the models, understand what Gemma is, how to actually understand the specifications of a large language model. So my goal is to not just talk about Gemma, but whenever you read up on any new model going forward, you could actually use some of these knowledge, some of the learnings from this session to understand the parameters of these models. So we are going to go a little bit deeper into the technical specifications of Gemma. And it might get a bit technical for some of us, but I think it's useful to understand what those specifications mean. We are going to then look at how Gemma was trained, how it was developed, some of the ideas behind training and development of these models. We will compare with Llama 2. I wish I had specs for Mistral. Hopefully when I publish the slides, I'll actually add some specifications for Mistral. Not all of them are public. And then we'll talk about how do you access Gemma and how do you develop applications using this model family. So that's the goal for today's session. So let's dive in. What is Gemma? Gemma is a family of lightweight open models that are built from the same research and technology that Google deployed to create the models called Gemini. Gemini is one of the most powerful model that is out there right now, or model families that's out there right now with Gemini Pro and Ultra. And the same technology was used to create Gemma. So what's the difference? The difference is while Gemini is a very, very large, massive model, this particular family called Gemma is basically a miniature version of it. So it's the same technology or similar technology, but this is an entrant into the small LLM space. And we'll look at what the small and large mean. But before we get there, it is by virtue of it being small, it is text to text only. So it's not multimodal. It is not going to create images for you, videos for you. It's not going to identify or caption your images, and those kind of use cases are not here. It is also not multilingual. So some of the other smaller models are multilingual. And obviously, most of the large models we see today are actually supporting multiple languages. But this is a small model, and it's focused only on English. We'll see why. However, it does give you state-of-art performance, sort of performance on many benchmarks, and we'll see some of those benchmarks. But you have to remember that you are comparing Gemma models with models of comparable size. So you're not, it wouldn't be realistic to take a Gemma model and compare it with GPT-4 or Gemini Ultra or Pro, for example, right? So we are talking about a model which is small. And ideally, the small size is a model that typically can run on a fairly small machine. So if you have a fairly good GPU or a laptop with a good GPU, like a A100 plus, you should be able to run the Gemma model on your laptop. So it's very suitable for low resource environments or even private cloud environments where you want to make sure that you can actually deploy fine-tuned models for your own application and inject your own company's data into it and keep it private, localized into your environment. So back to Junling's question, we often work with companies that say we are worried about sending data to the cloud. Like, we are not sure if the data will be used. Maybe we are not necessarily sending it properly, or it is potentially going to leak into the internet. Will the LLM provider use it for training their own models? And these are the questions that these cloud providers are answering. OpenAI, Microsoft, Google, and others are answering. But a lot of customers of those LLM models are still not convinced about data security. They do have some valid concerns about it. But here, you can actually take those models and deploy it on a small or relatively small server. So you don't need massive GPU clouds for deploying these models. And I have listed some resources here to end. So essentially, this is a fairly, and we'll go through some of these resources, fairly new announcement. And there are really good blogs, documentation, as well as notebooks available from Google to actually go and start using this model. And we'll visit all of that pretty quickly. Let's take a slightly deeper look at Gemma. Gemma was trained on a vast number of tokens. And as I said, it uses a similar architecture, but it also uses similar data and training as Gemini. So let's talk a little bit about number of tokens. As we have seen, there has been a push towards larger and larger models. The model size is often expressed as the number of parameters. And many models are now hundreds of billions of parameters, right? 175 billion parameters is very common. Now we are getting into trillion parameter models. And obviously, to run these models is not easy. You really need Google's scale to be able to run something like Gemini, or OpenAI scale, Microsoft scale to be able to run a GPT-4. So it's not realistic for us, like small companies, medium-sized companies, to actually take a model which is like a trillion parameter model and run it in your private cloud. But these are very, very small models as compared to those. So for example, this Gemma comes in two variants, 2 billion parameter and 7 billion parameter. So that's actually very, very small, right? So that's one thing to understand. But as the models were trained with larger and larger parameter sizes, one thing that was noticed was a lot of these models were actually undertrained. So as you saw with the chinchilla paper that I think we discussed here before, more data is actually leading to more data. I would say pre-training with more data has been leading to better and better outcomes. So in fact, Llama and Llama 2 have been really good examples of small models. So the number of parameters is small, but the amount of data is trained on is very large. And we have seen that Gemma takes this even a bit further. So again, two models, 7 billion parameters and 2 billion parameter models. However, each of them also come in two different variants. There is the base model, which is not fine-tuned, and the IT model or instruct-tune model, which is typically a fine-tuned model based on human interactions or some kind of a question answer prompt response kind of model. And we'll see how both SFT and RLHF are used for instruction tuning. So this is the instruction tune models are really good fit for interactive dialogue kind of applications, and base models are not fine-tuned, but the benefit is you can then fine-tune it for your own specific applications. And now you will see that most of the open models where you have access to the weights are often coming in these two variants. They come in different sizes, like for example, Llama 7, 13, 33, 70, and beyond. And you will also see that these models are coming in base and instruction tune variants. So if you ever go to Hugging Face or any of the sources for these models, you will see like Llama will have like 6 or 8 different variations that you can use, right? So which one would you choose then? You have to really be careful about, are you going to fine tune it? Do you want to use it for chat kind of applications? So that's one thing to decide, base model or instruction tune model. And secondly, you want to consider how big of a model can you run? Obviously, the bigger the model, typically you're going to get a better performance, but that performance also comes at a cost, because even at inference time, you're going to need quite a bit of memory to run even a 33B or a 70B model from Llama 2. So Gemma is what Google calls an open model, which means the weights are available. You can download the weights. It also allows you to have those weights and use those weights free. You don't have to pay for it. It is free for both commercial and research use, like Llama 2. Remember, Llama 1 was not available that way. But now you can actually take those models, you can tune those models, you can distribute those models with pretty much very minimal limitations. The limitations, I'm not a legal expert here, but I did go through some of the details there. The limitation basically says, don't use it for doing anything illegal. I mean, that's kind of pretty much it. Remember, if you or if you have tried to use Llama 2, you can also download those weights. You can play with it. But Llama 2 had a condition that said, if you had above certain number of users in your system, you are not allowed to directly use Llama. You have to kind of license it from Meta. And that was, it seems, primarily aimed at stopping large other big cloud companies like Google from just taking Llama and like doing whatever they want with it, right? So Google's Gemma actually take away that restriction too. So you could, even if you're a large organization with millions of users or hundreds of millions of users, as long as you are doing something legal with it, you can use it. But of course, you should go through the legal license to go through the use cases and your use. But as long as you're using it for standard legal stuff, just go ahead, download it. There is a link here that I have provided for Google open source blogs, and it explains the difference between open source model and open model. So this is not open source in the traditional way of calling things open source in software. So that's why they have chosen a slightly different term called open model. Let's dig a little bit deeper into how the model was trained and how it was developed. So as we know, all of these large language models are nowadays using standard transformer architecture. Gemma is no exception to that. We are looking at a transformer architecture with decoder only. So no encoder stack that we typically see in the transformers diagram, no encoder left stack there. As I said before, it was trained on a vast amount of text. In case of 7 billion model, it was trained on 6 trillion tokens. That's a lot of words. Each token is typically you can think of it as like a word. It's typically smaller than a word, but 6 trillion is a lot of training data. This is, and remember, Llama was considered as taking it to a large amount of data for pre-training, and that's why leading to better inference time costs. This is taking it even further because now you're using 3x of Llama's training data, takes from 2 trillion to 6 trillion tokens, massive training data. But only English, not multimodal, not multilingual. So it's not trained on audio, it's not trained on images, videos, and anything else. The source of this training data has been mostly web documents, code, math, like standard code from GitHub repos, we are guessing, and math, etc. One of the reasons why we wouldn't call it like fully open source is that you actually don't have access to the original data sets on which Gemma was trained. So I believe, if I remember right, Llama 2 also is much cleaner about what kind of data they trained on. And in terms of licensing, it was fairly clean and transparent that Llama 2 is using all of the openly available free data, pre-training data, like open source books, Wikipedia, and other sources. I don't think Google in its technical paper is as clear about what kind of data they have used for training and whether it is all free of any encumbrances in terms of usage licensing and those kind of things. It uses what's called a sentence speech tokenizer, which is same technology as Gemini. We can go into that detail if we have time. The other interesting thing is it has a vocabulary size of 256K words. So in some ways, you can think of it as how many different terms or parts of words can the language model identify. Llama 2 had a fairly large size, but it was still only 32,000. Here, we are looking at, again, much bigger, 8 times bigger vocabulary with Gemma. So I'll pause here to kind of quickly summarize this. Essentially, we are taking this transition or this idea that the Chinchilla paper, Hoffman et al. Kind of published, and we are taking it further from Chinchilla to Llama to Gemma, where we are training the models and larger data sets. And we are increasing the vocabulary size also. And we are finding smaller and smaller models that are actually performing better and better as compared to your previous models through more training and a higher vocabulary size. So my guess is that with Gemma, you are seeing a higher performance from Llama, not because of any major algorithmic breakthroughs. If you look at the Gemma papers, you will see that they are referencing a lot of paper like research from 2023. And as we know, Llama was trained early 2023 to I think early summer of 2023. So of course, Google has the benefit of kind of starting later and using the latest research, but I didn't see anything that was drastically different in Gemma's architecture or in terms of the application of different components or algorithms there. Obviously, there are slight enhancements, but most of the model improvements, I believe, are coming from the amount of data and the vocabulary sizes. Some other interesting things to note. Google is actually training these models on TPU hardware. So that's very interesting that we are not using NVIDIA GPUs for everything nowadays. And full LLMs, fairly large LLMs, can be trained on TPUs. They use TPU v5e versions. And in terms of the software, they are using a single controller programming model. It's basically kind of, you can think of it as a single Python program to kind of really train all of these models, which is also fairly interesting if you're looking at how the pre-training is done. To quickly round out the training part, there is a requirement for some of the pre-processing for the data. So Google has been a bit extra careful about what kind of data has gone into the trainings, and they have been filtering out at different levels to prevent toxic materials from getting into the model. As you know, LLMs can be hallucinating, but they can also create toxic material. And people have been sometimes using devious means to kind of get models to say bad things, racist things, bad stuff. So Google has been very careful about that, and they actually put a lot of emphasis in the paper on ethical use and precautions that Google is taking to avoid that kind of usage and support responsible AI. In this case, they are removing CSAM filtering, which kind of takes care of some of the child abuse kind of material. They are also filtering out sensitive data, such that personal information, such that it doesn't enter, your mine information is not kind of getting into these models. And then obviously they want to filter out evaluation sets. So they are not kind of acing the test because the model has already seen the answers. So evaluation sets are obviously filtered out. Let's go to the bullets on the right side. We're not going to go through all of these. These are fairly technical details, but the context length is 8192 tokens, which is fairly large. It is using a multi-headed attention. We'll see some of that detail on the next slide. Whereas 2B is using multi-query attention. It is using rotary positional embeddings, which is also similar to Llama. However, for the activation function, it is using something called as gglue, and it is different than what Llama used, which was swiglue. And as you might know, when the original paper came out, this is the Attention is All You Need paper from Vaswani et al. We saw that when the multi-headed attention is, or in any cases where you are actually doing a linear transform, you have to actually put a nonlinear function on top of it, right? Because if you put one linear transform on top of another linear transform, the effective outcome is like a single linear transform, right? So you obviously have to put a nonlinear function in between. And what the original paper did was essentially just presented the rectilinear unit function, which is like 0 if the y is negative and y if y is positive. In this case, in the case of Llama, we used a function called swiglue, and Google has changed it to gglue activation function. I can talk a little bit about that, but these are, I think, minor details, because if you look at the glue paper, which is gated linear units and some of the enhancements like Gaussian error linear units, those papers, if you look at the performance numbers, there is not a huge difference between swiglue and gglue. So I feel like this kind of is a different algorithm, but not necessarily driving any important major enhancements to the outcome because of the nonlinear function. And then we are obviously doing normalization of input and output of each transformer sublayer, which is also very common. And then once you do the base training, the instruction tuning is done in 2 steps. The first step is supervised fine-tuning, SFT, which is done on text-only data, both human as well as synthetic data, which is created by LLMs. And then Google is checking for some of the capabilities like, is the model following instructions? Is the model responding to facts? Is it being creative to a certain extent? And is it safe? And then it's using RLHF, reinforcement learning, with human feedback on top of the outcome of the SFT model. So SFT, RLHF. And in both these cases, this is something I found interesting. Google is also using high-powered, high-capability models to rate the outcome of the model that is done, the outcome of the actual Gemma model. So Gemma model outputs something, And the rater is actually some other model. So which is also model kind of evaluating and assessing the outcome of another model. So I'll pause here. I want to bring your attention to two important sources at the bottom, and I will open up those sources at the end. But there is a really good Google DeepMind paper on Gemma technical report, and it actually lists out what is Gemma doing, what kind of algorithms it's using, why, and it also lists out a good set of performance benchmarks and safety precautions that Google is taking. And then there is a Lightning AI paper, which I found was I think this is Sebastian Rashka, in terms of how do you understand these models and how do you fine tune the Gemma model. So I would strongly recommend going through both these links once we distribute the slide deck. Cool. This is a quick summary, I believe, of the parameters. We already spoke about models. One interesting thing is Google is not fully transparent here with the model. They call it the Gemma 7B model. But if you actually look at the model parameters, take a look at the right table 2, right model at the bottom, and look at the 7B row. It has 786 and 7.7B. So if you add the total number of parameters, it's actually 8.5 billion parameter, but they don't call it an 8.5B. They call it 7B, similar to Llama. And their 2B model is also almost like a 2.5B model. I wish there was like, a more forthcoming mention of this, but if you just add up those numbers, you will find that they're not really a 7 and a 2 billion model. I actually downloaded these models and played with it, and I actually printed the model summary, which you can do through standard Google Colab notebooks. And my model parameter count is actually different than what is published in this paper, which is kind of a bit surprising, but maybe they released a slightly different version of these models. Another interesting thing that I found here, and this is maybe something if there are any Google experts here in the audience, or anybody who is kind of really deep into transformers can help me understand this, it would be really good. But look at these parameters on the right side, right? Let's kind of quickly go through these parameters a little bit. Now we have, so we have the D model, which if you remember the original paper, that is basically the dimensionality of the representations that get into the multi-headed attention. Let's take a look at the diagram from our favorite paper. Attention is all you need. On the left is the encoder, on the right is the decoder. So for this paper, for Gemma, we are going to look at the right side. So you take input embeddings. So the input and the output dimensionality that goes into the multi-headed attention is the D model. Dimensionality of representation used as output. Now, of course, what happens is if you look at the arrow that goes from the input embedding and goes to the box called add and norm, you know that when you get the outcome of the sublayer, you take that sublayer of X, let's say X is the input, you run the function called multi-headed attention sublayer. So let's say sublayer of X, and then you add the original X to it, and then you do a layer normalization. So you do layer norm of like X plus sublayer X, right? And that is all from the original transformer paper that all of us probably have read. And obviously, because of that, your X and the outcome of X have to have the same dimensionality. So this D model, in this case, 2048, for example, is both MHA input and MHA output dimensionality. Layers is the number of substack layers that we have, right? So two sub layers, and then that forms one complete layer. And then you're going to stack up 18 of those for the 2B model and 28 of those for the 7B model. The feed forward hidden dimensions is, where is our diagram? Yeah. So if you look at the third box here called feed forward, that is that dimension, FF dimensions, and that is about 49,000 dimensions here. And then obviously those two are the sublayers, and you have 28 of those sublayers. So that is the structure of this model. The positional encoding is the rotary positional encoding for the Gemma case. Now, here is my question, if anybody can explain to me. In our standard understanding of these models, you have the input D model, and then it is distributed over multiple heads, right? So if you have D model and it goes into the N number of heads, the actual head size should be the D model divided by number of heads, right? So let's take a look at this. So 2048 divided by the number of heads 8 will give you the 256, which is mathematically correct, and it conforms to what the attention paper says. What I found a bit curious was that the 7V model actually does not follow that rule. If you divide 3072, which it claims is the dimensionality of the input to the MHA, and if it really has 16 heads, then 3072 divided by 16 is not 256. And I don't know where that comes from. If anybody has any idea, I would know. You can type it out in the chat box, or we can discuss it later. But this I found very curious. Either it's a typo, or it's an error in my understanding that I would like to clarify with someone from Google. Junling, if you have any comments on that, am I missing something, or is it?
I believe it's a typo because it should follow the convention, and the 2B follows that, right? So
Yeah,
there's no reason 7B should be different.
Exactly. And I have not seen any model card yet where this has not been true. But I also find it hard that Google, with all of its like massive brain power, publishes a technical paper that goes through dozens of reviews and publishes something with this big typo. So I'm like, maybe I found it wrong. I find it hard that I would go open up a paper and find a big error like this, because this is a fairly foundational parameter for any LLM. But this is likely a typo, and the real number should either be head size is 192, or the dimension should be 256 times 16, which is, I think.
Yeah, the reason is most people don't care about the head size. We don't normally report head size. We only report head and the D model. So for them, this is just a derived number.
Yeah, but you have to derive it with the 3072 divided by 16. Sure. And that is not 256. It is, I think, 192 or some number like that. But just kind of curious observation. Hopefully Google corrects it, and it's a typo and Google corrects it. All right. So I hope this kind of a bit of a deeper dive, for if you have not followed the transformer architecture till now, this might be a bit dense, like, complicated. But if you have just done a little bit of research on transformer model, I think this actually helps you understand how to map a model card to this architecture. So next time you open up any LLM model card, I would recommend opening up this diagram and then mapping up the number of layers, feed forward dimensions, the model, number of heads, and the encoding to understand how this actually flows through the complete stack. All right, let's go and look at Gemma and Llama 2 model comparison. For fun, I actually also put together the original transformer paper, Attention is All You Need. So that was the reference implementation. I put the numbers from that paper also. And you will see how fast this architecture is actually becoming fairly complicated, even for small models. Now, we are not even comparing with anything like GPT-4. Those numbers are massive. But this is a tiny model comparatively. But from 2017, I believe the Attention is All You Need Transformers paper came out. We have moved from 6 layers to 28 and 32. So Gemma is actually having fewer layers than Llama, which is interesting.
So for the original model, do you only consider decoder? The original model has both decoder, 6 decoders, 6 encoders.
6 and 6, yeah. It had 6 encoders and 6 decoders. So I just put the decoders here because this Gemma and Llama is only decoder. So the 28 and 32 are decoders. So 6 would be the right number to compare, right? Because the 6.
No, what I believe is we should consider as 12 layers because now the decoder, since they don't have encoder, act almost like encoder.
Yeah. I think that is also fair. But even with that, I think we are clear that we are actually stacking up these models pretty tall. The dimensionality of the embeddings is now increased from 512 in the original paper to about 4096, which actually I believe is also the dimensionality of Gemma. Number of heads has increased from 8 to 16 and 32. And the head size is substantially bigger at 256. So, but the most interesting thing is the vocab size is massive at 256, which means the model is actually able to process a wide variety of tokens, and its comprehension of tokens is actually growing really well, or becoming fairly complex. Finally, the feed-forward hidden dimensions have increased substantially from 2,000 to 49,000 in Gemma 7b. And we are actually seeing very interesting research about activation functions between the two Ws there. And we are kind of, I think, seeing some kind of plateauing of gains by moving away from ReLU in general. This at the bottom is the explanation of SWI-glue and GE-glue. I don't think we need to get into that. The rest of it is, I think, something we have covered. So let's get into performance comparison. This is from Hugging Face Open LLM leaderboard. I took it a few days back. I believe it's also part of the Hugging Face blog when they announced Gemma. So these numbers today would be different. I was traveling this week. I didn't get to take the latest screenshot, but this is available for anybody to go and look at. And as you would see, Llama 270B in terms of open LLMs still leads the pack. It's obviously a much bigger model. And right after that, you see Gemma is actually getting a lot of interest with a very high leaderboard score of 63.75. As we saw before, the token size is 2 trillion and 6 trillion for the two. So a larger token size even than Llama 270B. I think the one interesting entrance here is from MIT Microsoft's Spy2, which is trained on a fairly large number of tokens as compared to the model size. It's also a 2.7 billion model. And then Gemma 2 billion is actually just making the cut in this case at a fairly low score. But also remember that it's a really, really tiny model. You can absolutely run it on even an old laptop that you may have lying around. The quality of Gemma 2 billion model is, however, pretty questionable. So if we get time, we can go through some of the actual, we can run some inferences on Gemma 2 or Gemma 7, but you will see that Gemma 7 actually produces fairly good results. Gemma 2 results, I was actually fairly surprised and kind of not super impressed with. Capability scores, I have picked this up from the Google's technical paper on Gemma models. As you would see, the blue is Llama 2, 7 billion, and the green line, the green bar is Gemma 7 billion. So they are actually the most comparable models in capability, like sizes in terms of parameter sizes. But you will see that Google claims that their model is much superior on math and science. In fact, it's far superior to all comparable models, including the larger Llama 2 model, which is 13 billion parameter model. And it is equal or fairly equal or slightly better on reasoning and Q&A. Gemma 2, however, seems fairly less capable model. It's not here, but in terms of performance, its performance numbers are fairly low, which is also expected. But what surprised me was the Phi2 model actually outperformed Gemma 2. And I don't know why that is so, but it is a very interesting result. Let's take a look at some performance numbers on SOTA performance on automated benchmarks. The most interesting is the MMLU, which is a massive multitasking language understanding. And Google claims that the 7B model is far superior to other models. The one that is close enough is Mistral, which, as we know, was the leader out there till now. And also HelaSwag, which is reasoning, and it's also done really well. So according to Google, the Gemma 7B outperforms Mistral on most parameters and Llama 2 on pretty much everything except the trivia Q and NQ multi-shot or few shot learning benchmarks. Now we can jump into how to actually access and use these models. Gemma is available through multiple ways. Google has actually made it very easy for all of us to go and use Gemma. So you can go to Hugging Face and download the model weights. You can go and use it on Google's own Vertex Garden, and you can use it also from Kaggle. I also tried a simple OLlama method that also worked, but I did it about 7-8 days back, and I haven't tried it in the last few days. So I don't know if something has changed there. But if you have access on any of these methods, just go and use. I would recommend Vertex AI if you have a proper corporate account, or if you want to open a free account with $300 credit. Otherwise, Hugging Face and Kaggle also, of course, let you download the model weights and play with it. So for Google's own Colab, there is a Kaggle notebook that's available that lets you use Gemma with Keras NLP. And you can actually click here on ai.google.dev, the Gemma docs get started. It will actually open up a notebook, basically a Colab notebook that will explain to you how to set up and how to run these models. And if we get time, we can do that. So what are the steps to do that? Go to Google or go to Kaggle. And this is one way. You can, of course, do it using other ways on Vertex as well as on Hugging Face, but I'm explaining the way to use it using Keras on Kaggle. So go to Kaggle, sign up or sign in if you already have an account. You actually have to request access to Gemma. If you have played with Llama last summer, you've probably gone through that process. I believe Llama, when it launched, it kind of was glitchy in terms of access. I could not get it to get approved quickly. And then they sent you an email, and that email had a unique link, and it was kind of a little complex. Google has made it super easy. Everything worked for me super smoothly. Literally on the day Google launched, I jumped in, played with it, had zero glitches. That was not the case with Llama, but obviously Google has the benefit of learning from Llama 2's experiences. So you access Gemma through, you make a request, you get instantaneously approved once you sign up and approve and agree to their contract or agreement terms and conditions. The interesting thing is you have to open up the Colab notebook, and typically on the right side here, you will see that you have to change the runtime type. They recommend you run with a T4 GPU. I was able to run it on a Google Colab Pro, I believe, with 800, but most of the time the V100 with a 7B parameter failed for me. So if you're playing with the 7B parameter model, which is the larger model, I would recommend using A100 or a better process and preferably a higher RAM option. If you're playing with the 2B model, then probably any of these options should work just fine. Then you go to your Kaggle and you go to your account. So on the Kaggle, you will see your profile, go to my profile, click on settings. And then here, it's not very clear because of my footer here, but you will see a button called create new token. So you create a new API token, and then you go into your Kaggle notebook, Colab notebook, and enter those username and the key as your secrets in your IPython notebook, the Colab notebook. I have just taken some screenshots. So if you are actually following my guidance here or following Google's, you will be able to see exactly what it looks like or what it should look like on your screens. And you should be able to, on the right-hand side, bottom, you will see that the Kaggle key and the Kaggle username are the two variables you created. So very simple. There are multiple tools for inference and fine-tuning of Gemma. If we get time, some other, like maybe towards the end of the month or early next month, we can have a quick session on how to actually fine-tune Gemma and how to kind of do it with Gemma-specific formatting of input-output. But suffice to say that you have access to Gemma with PyTorch, JAX, like Google's own TensorFlow, and native Keras 3.0. You have Colab Kaggle notebooks available. There are links that I have provided here. Click on these links. Fairly good, easy to follow instructions. Typically, most of these things should work for you. But when you run the Collab notebook, you will see some weird errors and you just have to work through some of those things. But for me, about 80 to 90% of the time, it kind of went pretty smoothly or the errors did not matter. You also can deploy pre-trained as well as instruction-tuned Gemma versions on Vertex AI with GKE with Kubernetes. I would personally recommend using Vertex AI for any like private cloud deployments. If you're at a company account, you want to deploy something for fine-tuning with your company data, I would recommend opening up a Vertex, a Google Cloud GCP account using Vertex AI, and then using Gemma or Llama over there. But for your own fun, playing experiments, proof of concepts kind of things, if you have a fairly decent GPU, you can use that, or just open up a Collab Pro account, $10 a month, and you should be able to play with these accounts. Finally, the integration tools are available with Hugging Face, MaxText, Nemo, which is NVIDIA, TensorRT LLM. Let's actually take a look at a notebook. Tell me if you can see my screen, which says Zoom.
Yes, we can see.
Cool, because sometimes I switch screens, it kind of goes away. So let's walk through a few things here. Number one, look up this link. It's all of these links are available in my presentation, but if you just find like Google Gemma, probably this is going to be the first, second link, and then introducing new state-of-the-art open models. Go through this open models. Very good focus on responsible Gen AI toolkits available on all these different platforms. Some of the metrics here. And as I said, free credits with Google Cloud. The report I mentioned is also available here. I have provided you the link for that. Interesting things, some really good history about how it started with sequence models, transformer models, and some other interesting research. Some of the metrics and performance models, specs that we talked about, how they pre-trained it, filtering of the data, CSAM and other things, instruction tuning, and then this is the format, very similar to what you would do with LangChain or OpenAI's, three-role model, user, system, AI, everything. So all of these kind of similar format with end of sequence tokens and other things. Interesting paper, and I think this session will give you a high-level overview, but it is worth kind of going through the details in this paper if you're interested in learning more about the models. So as I said, there are different ways of accessing Gemma. One way is to actually go to Kaggle, sign up, go through the model card here. There is a very interesting CPP library and some really good sample code. You can run it. The other option is to go through the get started using Keras NLP link. You can run it in Colab, Vertex AI, or obviously there is a inference kind of sample code available on GitHub. Any of these three methods work. All of them worked for me, but obviously the easiest one is to open up a Colab notebook. As you can see, I have a Colab Pro here. That is, I would recommend using a Collab Pro if you can. And then what you would typically do is go to File and create your own copy. That way you can change and store your own credentials. So I created my own copy. Let's quickly walk through this. Here, you would actually select a runtime. So I would go and maybe select a A100, right? I don't know if we have time to run all of these. Some of these steps take longer, but I'm going to walk you through some important ideas behind how to run these models, you can actually cut and paste your code in your own Python file and use your own IDE like VS Code. Just works just fine with very, very small changes, obviously with related.
Unmesh, can you make the font a little larger?
A bit bigger, yeah. Is it helpful?
Yeah, much better.
Awesome. So basically something like a .env, you read local environment parameters. In this case, I've actually stored the secrets here in my Collab notebook, but you can obviously read it from your own env file. You can do a standard pip install for Keras NLP. And then you have three options: JAX, TensorFlow. Here is actually, before we go ahead, here is what you will sometimes see. Like, for example, I just said, run this, and it's going to print my own environment variable, Kaggle username. I'm not printing the Kaggle key, of course, but you do an install, you will actually most of the time see a weird error about pip not able to resolve things properly. I have found this error kind of pretty benign, so don't worry too much when you get this error. It will probably just work fine. Then you go and do either a JAX, TensorFlow, or Torch. You can just uncomment, like I just added more lines here. You can choose whatever formats you want. Right now, I'm going to use JAX. Here is the interesting piece of the code now, right? So here they are using the Keras NLP.models.Gemma causal LLM from preset. So this is basically an existing model, and this parameter will tell which model to use. I'm going to use Gemma 2B here because Gemma 7B is a fairly large model. It will take a long time to run or even like download. So this is going to take a little time. By the way, when you go and create your own credentials, you have to download a JSON file with those credentials and import it into your notebook. This is fairly standard if you use Collab. So this is the step where it's actually going to download everything, and that takes typically a minute or two, depending on how fast Collab is working. I will let it download, but here is something interesting. I've run this already, so the outcome is here. But you can download the Gemma LM, and you can run this simple method called summary, right? And it's going to print a nicely formatted summary of how many tokens are there in the vocabulary and some other parameters. You can see that the Gemma backbone has 2.5 billion tokens, and the total embedding tokens are 500 million out of this, right? So what I did was I went to the paper and I took the actual number of tokens in the paper, which in this case for the 2 billion model is this 19 starting, and the 524. And my number actually came out slightly different than what they have published here. Okay, slight discrepancy, little interesting thing, nothing too much to worry about. And now we get to do some fun stuff. Gemma.generate, here they will actually provide you like some standard stuff, right? So I think they do like so now what has happened is the model is actually downloaded, and this earlier line, causal LLM, is basically downloading the model, and this now language model is going to predict the next token based on the previous tokens, like the standard autoregressive thing. So this question, of course, because it's an LLM, is going to give you different answers at different time. In this case, it said Life 101 is a 10-week course that is designed to help you understand the basic of life. It's a course that whatever. Like, I don't know if it is a true answer for what is the meaning of life, but it found something that it was trained on, and then it spit out the answer. If you run it again, you are likely to get a different answer. What I found, yeah, here it is, right? You got a different answer. What is the meaning of death? What is the meaning of love? What is the meaning of freedom? Now, one thing I found very kind of surprising and not so encouraging about Gemma is despite Google's all the big research and training and all the techniques, this model is doing what is called as LLM repetition. So as you know, LLMs have this tendency to keep on repeating the same thing over and over again or with slight variations. But there are standard techniques that all of us have learned in NLP and NLG in particular to avoid that, right? I forgot, but there's like this nucleus thing, there's a top K, there are nucleus sampling, top K. There are different methods that you can use to make sure that the model doesn't keep on repeating it like a baby, right? But somehow Google does not seem to have done a lot of that. And a lot of outcomes keep on saying the same thing. For example, what is the meaning of love? What is the meaning of freedom? It actually is not answering this, but it's kind of continuing the auto-regression. I'm not using fine-tune instruction-tuned model here, right? I think the answers will be better if you use that. I asked it to do a haiku poem with each line starting with a letter. It actually did a fairly good job, but look at what it is doing here. A haiku is a Japanese poem, so it actually defined what is a haiku. Then it says, here are 3 haiku poems with the first line starting with letter A. But that's not what I asked it to do. I said each line starting with letter A. I did not ask it to do 3 haikus, but here is what it did. A lone apple tree stands in the garden, but then it created a second haiku, which basically is pretty much the same. And then it went to the third haiku, and it kind of did again the same thing, which is, I feel like we have gone past the repetition problem a long time back. I was surprised at the lack of quality from Google's 2B model. I did see a much better quality with 7B. So don't judge this whole family with the outcome of 2B. 2B is a really tiny model and it's not very capable. You will definitely get better outcomes with 7. But I was surprised that it did not understand a simple instruction like this. But if you do an instruction tuned model, you will see much better outcomes. Then here is an interesting thing. I mentioned, I think, top K or nucleus sampling. Here, you can actually use different sampling techniques. There are a few samplers available with this link. But in this case, you can actually compile it with a slightly different sampler. By default, it's greedy, but I'm now compiling it with sampler top K. And here is the difference, right? Greedy, so when the natural language generator is generating different outcomes, it associates probability with each of them, with each of the outcomes. The greedy algorithm is only going to take the one with the highest probability, right? So if it's like a 0.6, 0.3, 0.1, then it's going to take the one with 0.6, and the other 2 are ignored. With the top K, it does slightly different. It chooses, let's say it's creating an outcome of 20, and you say top 3, it's going to randomly pick one of the top 3. Right? So it's not always going to pick the highest probability outcome. What it does is it gives you much more variability in terms of the outcome. And then when it goes back, obviously, you get much variable outcome, which generally leads to more creative, less repetitive outcomes. So this is, for example, one quick so I typed, how does the brain coordinate with body's organs? And I found some very interesting answers. Let's run it right now. By the way, this is actually a very simple tutorial. So within 30 minutes of this session, if you're interested, you can literally go and do all of this. Fairly easy to do. And it's a lot of fun to compare the 2B and the 7B outcomes. Here is something that I found very disappointing with 2B. A lot of times, it actually prints out some internal model stuff. In this case, it is probably doing some level of masking tokens or some delimiters or whatever. But a lot of times this output made 0 sense. For example, in this case, it says plants are adapted for, and it kind of keeps on repeating the same thing. No idea. If I were running this program at Google, I would be very disappointed and I would be very careful about publishing this. It looks like Google has rushed out the 2B model and the 7B model is better, but I'm surprised at this quality, for example. This should not happen from Google in my mind. After you complete this, there are some really interesting tutorials for fine-tuning Gemma and then distributed fine-tuning, and then how do you actually deploy it in Google's own Vertex model garden. And hopefully at some point we can actually go and play with these three things. And I can show you some real life examples of how do you build and deploy these models in real life applications on a platform like Vertex. I'll stop here. I hope this was useful. And let's open it up for a few questions.
Thank you, Unmesh. Now, feel free to unmute yourself to ask a question. All right. I can start with my question. As we can see that the smaller model has lower accuracy. So you mentioned about in the beginning that for enterprise, they want to implement in-house their own small model. But do they worry about the accuracy? How do we remedy that? I mean, most small model don't have a stellar.
Yes, so that's a very valid concern. Now, what I showed right now was a couple of things, right? Number one, this is the base model. Base models are not really meant for human-like interaction because they are not fine-tuned for that interaction. They have not been they haven't gone through any kind of RLHF where the humans have taught the model what is a good answer and what is not a good answer. So you have to kind of remember that the model's outcomes that I showed is reflecting some model that is not even like really instruction tuned. Having said that, I feel that the model that at least the base 2B model is not really ready for a production deployment. I'll give you some examples here. So I asked this question, how does the brain coordinate with body's organs, right? And here is the answer I got. The brain is the control center. Now, I'm not going to read all of that, but look at these words. Center, it is the center of nervous system. It is the center of endocrine system. It is the center of. So it is not really responding in a human-like manner. It is also, I highlighted this, it is also repeating the same content 4 times right here. In some cases, when I say, how does the brain coordinate with body's organs with the top case sampling? So if you don't do top case, you're always going to get this answer. But if you do top case sampling, you are sometimes going to get a very curious observation where you actually get what I believe is Google's fine-tuning. All right. So it actually publishes literally 4 options and it says the correct answer is this. Which I believe is what's happening here is some of the fine-tuning data or some of the training is actually leaking into the outcomes as it is. In this case, for example, it created for me 4 answers, A, B, C, and D. 3 of them are totally wrong.